Hello, I am Thomas. Clément and I are going to present our work to define a core hardware language amenable to formal reasoning about performance properties. This is a joint work with our advisors Adam Chipala and Arvind. First, let's introduce some hardware background. Hardware circuits are composed of state elements, the registers, and combinational functions, Boolean function implemented as a network of gates, describing how, synchronously, all the registers are updated each cycle. This description is precise, but difficult to manipulate and reason about. Let's study a simple processor design to understand why. Here is a diagram representing a 4-stage pipeline processor. The 4 stages of the pipeline simultaneously operates on 4 different instructions. So at the same time where the processor requests a new instruction to memory, it also decodes and reads the register for an older instruction, performs the arithmetic for an even older instruction, and retires the oldest instruction in the pipeline, updating the appropriate register. At the register level, the new rule for registers can be complicated. For example, the register between the fetch and decode stage that plays the role of a single element FIFO has a complicating update. It depends on whether the instruction can accept a new request, whether there was element in that FIFO, whether the decode stage will simultaneously consume the element in that FIFO and so make room for a new one, which itself depends on whether there is a free spot in the decoded instruction FIFO, which itself depends on whether the execute rule fired. In fine, the new value for that register depends on most of the design. Our approach is grounded in a different methodology. We use the rule-based methodology pioneered by the Bluespec language because it allows us to bypass difficulty due to that form of concurrency. In this methodology, the developer writes rules, fetch, decode, execute, without worrying about their concurrent interaction. It is the compiler job to analyze the rules and assemble them, automatically generating the difficult control signals. The compiler uses static analysis to discover parallelism opportunities between rules. It then assembles the rules in a circuit in any way it wishes, as long as each cycle the resulting update appears as if a subset of rules were performed one rule at a time. Hence, semantic of a rule-based program is defined as the non-deterministic execution of rules one at a time to cover any choice that could be made by a compiler. For example, the processor design is composed of a collection of 4 rules. Starting from an empty pipeline, represented here, we could execute the fetch rule and so fill the fetched FIFO. Then we could decode that instruction and so fill the decoded FIFO, and then execute it to fill the executed FIFO, to finally write back the destination register of that instruction and empty the pipeline. In that scenario, note that the pipeline always contains exactly one instruction. But we could have non-deterministically fire fetch at other moments. While we cannot execute fetch twice in a row, because fetched FIFO would be full after the first execution, we could fetch the fire rule after the execution of the decode rule. This way, we reach a state in which there are 2 instructions in flight in the pipeline. And so it goes with more opportunities of non-determinism. In the one rule at a time methodology, we worry about all possible executions. The design should be crafted to produce a correct behavior independently of what path of rule is executed. This way, when the compiler generates a circuit that performs several rules each cycle, we know that necessarily we considered that behavior in one of the paths of the semantics. So we saw that on the one hand, the register transfer level is precise and deterministic, but it bakes in explicitly all concurrency in the design, making formal reasoning particularly challenging and non-modular. On the other hand, rule-based methodology can bypass concurrency complexity, allowing to reason one rule in isolation to establish functional correctness of designs more easily. However, as we have seen, rule-based semantic is non-deterministic, such that one cannot even state performance properties. Indeed, the exact cycle-accurate behavior is depending on implicit choices made by the compiler. So we can neither state nor prove property like it takes exactly 4 cycles to execute an add instruction. Neither can we study timing side channels, such as the number of cycles that this core takes to compute its answer is independent of what is running on a second core. Our contribution is to design and implement a rule-based hardware language for which we can reason formally about which subset of rules gets executed each cycle. Our solution first introduces an explicit notion of schedule, a linear order similar to what the Bluespec compiler internally computes. But then, to realize that schedule, we dynamically track read-write sets of rules to discover and resolve conflict. Let's first describe an example, and then Clément will explain how this semantics can be efficiently realized as a circuit. Here is an example in pseudocode. The program is composed of two rules and a schedule controlling the order in which the rules should be interpreted each cycle. The schedule indicates that we first interpret the rule divide, which starts by reading register R. Let's assume that the value is 10, so V is 10. So this expression causes a log to be expanded from an empty log to a log containing a read R event. These logs get extended again when interpreted the second expression of the divide rule, which appends a write event to the log. 10 shifted by 1 to the right is 5. We then interpret the multiply rule, and the first subtlety in the semantics arises. Indeed, hardware registers don't behave like traditional software variables. They are only updated at the end of the cycle. So while we committed a write to register R, this write is not visible by subsequent read until the end of the cycle. Authorizing a read would result in observing the old value 10 again. We recognize the root of a linearization violation. That is, we are trying to read after another rule claimed that it is currently writing for that cycle in that register. So we stop the execution of the multiply rule, and we discard any contribution that it had made to the log. Now, if the value in the register had been 1 instead of 10, the interpretation would have gone differently. Divide would not have generated a write event, allowing the interpretation of multiply to go through and generate a write event 4, write 4.
Thanks, Thomas. Koika isn't just semantics. We also have a compiler. It takes as input a collection of rules tied together by a scheduler that arbitrates conflicts between those rules. It outputs a single circuit with one input and one output per register. The compiler's job is to bridge the gap between Koika and circuits. We're going to look at the two main issues. First, Koika's semantics track changes using potentially unbounded lists, and in circuits we only have finite resources. Second, Koika's semantics run rules one by one, but in circuits we want maximal concurrency. First, let's see how the compiler translates the logs used in the semantics into circuits. Of course, hardware circuits are finite, and so the naive unbounded log representation used in the semantics does not directly map to hardware circuits. But there's a trick. In fact, Koika uses logs for two purposes: recording updates to apply to registers at the end of each cycle, and tracking reads and writes to detect conflicts. For both purposes, a finite representation of logs is sufficient. Thus, our compiler translates Koika programs into circuits that track 2 bits per register indicating reads or writes, and some additional bits to record the values written. Here's an example. Suppose we have a program that writes an expression v into a register. We recursively compile v to get a circuit, shown here in green, and then we generate a new hardware log circuit, which records that a write has happened and what value it produced. Now for a second example. For a program that contains an if, we start by compiling the test in both branches, and we assemble the resulting hardware log using a white muxing circuit. The second problem is to introduce concurrency. The semantics of Koika specify that rules that make up a program must appear to execute sequentially. At the end of a cycle, all must be as if the rules had executed one by one, in the order specified by the user-supplied scheduler. Indeed, in the semantics, each rule is executed with the output of the previous rule as its own input, and the conflicts are detected right when they happen, causing faulty rules to be rejected right away. In the first picture, the highlighted OR markers indicate that Rule 2 and Rule 3 may have failed due to conflicts with previous rules. But since concurrency is essentially free in hardware, it makes a lot more sense to run each rule concurrently and to merge logs later on. Accordingly, our compiler translates each rule independently, producing one circuit that tracks reads and writes for each rule, but does not look for inter-rule conflicts. Then, we separately generate additional circuitry, which we use to reconcile the concurrently produced logs after the fact. Now that you have a sense of how the semantics in the compiler work, I'd like to talk a bit about what we've built and what we've proven on top of them, and how all these pieces come together. Our core object is Koika's semantics, which give meaning to Koika programs. We wrote them in Coq as an interpreter. Then, there are Koika programs, written by users of the language. They're typically written using a custom language embedded inside of Coq. Separately, users can write specifications of high-level properties that their designs should verify, such as asserting that a given program computes the right value or produces results in the right number of cycles. The semantics or what allows us to prove that these specifications hold. Then, we have the compiler, also written in Coq. Using that, we can translate our programs into RTL circuits. The compiler is verified. We'll look at the two key theorems very soon. The key advantage of verifying the compiler is that we now know that any properties proven about the original programs carry to the compiled circuits, including timing properties. Consider an arithmetic pipeline, processing an infinite stream of inputs and producing an infinite stream of outputs. With traditional one rule at a time semantics, the best one can prove is that the pipeline produces the right elements in the right order, but not necessarily at the right speed. Concurrency bugs, such as stuttering issues, cannot be ruled out. In the paper, we show how Koika's semantics can rule such bugs out. More precisely, we prove that with a pipeline FIFO queue in the middle and the right choice of scheduler, the stream of outputs will match the stream of inputs with an exactly 2 cycles delay. Koika provides very detailed per-cycle semantics, but often all you need in order to prove functionality is a coarser one rule at a time characterization, which guarantees that your circuits behave in a linearizable manner. So we've proven, in Coq, that Koika's semantics are compatible with a traditional one rule at a time characterization. You can use this to prove all sorts of latency and sensitive properties. But semantics are most useful when you can guarantee that your compiler preserves them, so we also proved that. The compiler is a few hundred lines of code and about as many lines of optimizations, and all of that is verified, producing circuits targeting a tiny subset of synthesizable Verilog. To finish this tour, let's look at a case study. Remember that processor that we started with to highlight how rule-based methodologies were well suited to pipeline systems? Well, that's precisely the example we chose to implement. We used it to answer 2 questions. First, can you actually use Koika to build real stuff? And second, what is the overhead of the dynamic circuitry that Koika generates? To write the RISC-V core, we started from a simple but time-tested Bluespec design, which we ported to Koika. We use the free toolchain for compilation and synthesis. We go from Koika down to Verilog using our verified compiler, and then we use free tools for synthesis. Our design passes the usual RISC-V tests and runs simple programs compiled with GCC RISC-V, including the one that I used to draw this picture in simulation. We ran in simulation using Verilator, as well as on FPGA. At this point, you may be worrying about the cost of faithfully implementing our semantics. Yet, once you look carefully at what dynamic tracking Koika is introducing, it's fairly easy to convince yourself that the cost is going to be minimal. There are 2 reasons for this. First, most designs don't make use of the extra flexibility that Koika's semantics provide over Bluespec, and in that case, there's a close connection between the static analyses that the Bluespec compiler performs on ASTs and the optimizations that we apply directly on circuits. Second, these overheads are easily measurable, so we did just that. We compiled our RISC-V core using our own toolchain and evaluated that against the same design written in Bluespec and compiled with a commercial BSV toolchain. The numbers on the slide show 2 sets of results, depending on whether we make use of a low-level optimization called register retiming. In one case, our design is about 15% slower than the Bluespec compiled one and occupies the same area, and in the other case, our design is about as fast as the Bluespec compiled one and 18% larger. Those results are from back when the paper was being published. Since then, we added a few more simple circuit optimizations, and the gap is now much smaller. Finally, just to make sure that you don't think we've exhausted all avenues for optimization and are showing the very best results that we could hope for, I've printed the complete list of transformations that we apply at the bottom of this slide. They're all very simple Boolean optimizations. Stepping back, where does this leave us? Well, first, we proved that it's possible to build semantics that accurately capture performance properties, that is, cycle counts, while preserving the essence of rule-based languages like Bluespec. Additionally, our experiments demonstrate that applying the resulting principles lead to a practical programming language. And finally, this work opens the door to many further applications. In particular, timing side channels are all about the effect of microarchitectural interactions influencing the cycle counts of the program. So Koika lays the groundwork for proofs of freedom from timing side channels. Thanks a lot for your attention. There's a lot more to read about in our paper, and we have tutorials and plenty of examples in our source repository. So give Koika a try.